that Mendeleev was able to figure out. Our Eka silicon were his predictions, and then germanium was the discovery after they found the element. That's what the properties that ended up coming out to be. So those are pretty spot on predictions, and it's that level of accuracy, which is why we kind of give Mendeleev a lot of credit. His ability to be able to predict these things was pretty phenomenal, and that's why he's known as the father of the periodic table. In his organization, he did go through and still keep it by mass. Okay? Why would he still have organized his periodic table according to mass? When was his stuff? 1870s? Why would he feel organized by mass and not by, say, atomic number? Because our current periodic table is atomic number. Okay?
That's all they knew.
What do you mean that's all they knew? Right idea?
There wasn't measurement of, I don't know,
What was the atomic number? The number of protons. When did we have protons? Early 1900s. They hadn't actually discovered nuclei yet. Okay? At this point, these were still just atoms. The elements, the smallest reduced part was an atom. Okay? So they didn't have an idea of atomic charge, okay, or nuclear charge. They just said there's an atom. Okay? So they didn't have protons to be able to organize it by atomic number. Okay? And if you go through and look, by atomic mass, it's not too far off. If we start with hydrogen, the very first element, its mass is 1. Helium is? Try again. 4. Okay, mass is at the bottom. Atomic number is at the top. So it does increase. Okay, and it's not a perfect increase, but we do notice that it increases generally across all of the elements. There's a few exceptions, and those few exceptions cause problems. Because people are like, well, the chemistry more aligns over here, but the mass says it belongs over here. Like something doesn't work out well. Okay? This is why you go back and watch the videos for those moments. Okay. Everybody watching the videos, like, what the hell's going on? So it wasn't until we actually identified that we had nuclear charge, that we had protons, neutrons, and electrons, that we actually get organization by atomic number. Okay? And that's Moseley, not a big deal, but that's Moseley, nuclear charge. Okay? The last big kind of periodic piece that came in was the discovery of our noble gases, which started with argon. Okay? Argon's right about here. All of the noble gases don't react, okay? Or they react very, very minimally. And because of that, if they don't interact with anything, how do you find out that they exist? You don't. Okay? It becomes a very challenging element to actually find and discover, and that was Ramsey, was primarily responsible for that. Okay? So that gets us up to our current periodic table. Periodic law, organized by atomic number. Okay? So that's the big thing. Our periodic table is organized by atomic number. Okay? There's lots of other organizations within the periodic table. Okay? And that ultimately narrowed down when we figured out something about where electrons exist. Okay? So the existence of electrons organizes the rest of the periodic table, okay, which is a very fascinating subject, but it requires a bit of deep thought and organization. So we'll hold for that for a moment and still go through and look at some of the other kind of big trends that we can pull out of the periodic table. Okay? When we reference it, we want to be able to reference each of the axes, if you will, of our periodic table. So we've got vertical columns, which we'll reference as groups or families. Those are used interchangeably. Horizontal rows are your periods or series. Okay? Also tend to be used interchangeably, though period tends to be the more common one, I think. I have a hard time with vertical and horizontal. Okay? So our vertical is that up-down axis, and our horizontal is the left-right. Okay? You're like, yep, you're an idiot. Thanks. I appreciate that. For those of you who didn't say anything, welcome to my party. Okay? Horizon. There we go. We could use origin, root words to help us identify those pieces. Okay? So now I feel like even more of an idiot that I didn't know that. So just add to it. That's okay. Horizontal. That's what you're here for. Helping is definitely helping. Okay? The next part that you get behind this is if we go through and look, you'll notice that some sections have more names. Okay? So for instance, that very first column, they call the alkali metals. Okay? Why might we call them the metals? That didn't come out very well. Why might we call them metals?
Because there's more than one type of metal. I need malleable.
Shiny and malleable, so we could look at their properties. They're all to the left of the staircase. And that staircase was our line between metals and non-metals. So they're all metals over there, right?
Generally speaking, right?
Nope, fully.
Fully?
Yep. The second column is our alkaline earth metals. I always got those confused. This is kind of a dumb mnemonic device, but it works. We said they're all metals, so let's get rid of the metal word, right? So ta-da, no more metal word. Jiminy Christmas. There we go. How many words for the first column? One. The alkali family. For the second column, how many words would I need to use? If I used one word to describe the first column? Two. So I get alkaline earth. Okay? I always thought that was cool. Well, always thought it was cool. I thought it was cool once I figured that that worked. Okay? So you are responsible for knowing those names. Not a huge issue. I made it through most of my chemistry career without actually being able to do that correctly. Okay? The next big section are known as the transition elements or the transition metals. These are not semi-metals. These are all fully metals, but they're transitioning between these first two columns and these last six. Okay? And that might seem kind of weird as a name, but that name has origins back to where the electrons exist. Okay? So the transition elements are helping us to transition those two main groups, the first two columns and our last six. The last six each have their own names, okay? And we'll address most of those, I think, on the next slide. But the two important ones are the halogens, fluorine through astatine, I think is what it's called. So fluorine, chlorine, bromine, iodine, you need to know is part of your halogens, and then your noble gases. Okay? At the bottom, we get our inner transition elements. Okay? And a lot of people have gone through, in fact, I had a geologist this semester yelling at me, oh, this is so dumb. Why did they organize the periodic table this way? It looks so stupid. Like someone just showed me that those elements, those inner elements, can be inserted up here. Because that's what they are. Okay? See La? La for lanthanide. AC for actinide. Okay? Those are pieces inserted into the periodic table. We have arbitrarily taken them out. Why might we have taken them out like that?
You have made it this much wider.
If we kept it in there, the thing gets stupidly long and rectangular. Okay? And so aesthetically, it looks awful. This way, it looks a little more square, and we can be happier with it. There's another reason why I kind of argue that those get pulled out. How often do we work with those? Rarely. Okay? So infrequently that we pull those out and kind of separate them and almost ignore them from the rest of the periodic table. Okay? So we don't see a lot of questions on those. You might, if you have to go through some more chemistry classes, get some questions based on those. But the only people that are probably ever going to work with those elements would be nuclear chemists or nuclear physicists. Everybody else doesn't care.
Have you ever worked with those?
I have not. Americium I have. Americium is, I believe, what actually makes smoke detectors work. So I've worked with it through smoke detectors. That's about it. Okay, so that's kind of our large organization. Another organization that'll come out of these. Okay, the naming doesn't quite make so much sense yet, but those first two columns are sometimes grouped together and called S. Okay, so they're part of the S block. Okay, They're making up kind of that rectangular shape. If we look through the middle, we have that transition element block, and we could call those a block too, but that's an awful lot of letters, so we can condense that to D. And then at this far right, this whole block is yet another block, and we can call that P. For those of you wondering how somebody already knew that, that's probably because they had enough chemistry where they addressed what these things were called. The bottom one is known as the heavies. F block. Okay? Those names have origin, or those block characteristics have origins in electron configuration. We don't know electrons yet, so those names don't really make much sense. But by that same token, is calling it the F block any different than calling it lanthanides and actinides? Not really. Okay? So we will see those names. You will hear me reference them according to those names because it is very, very important for how we go through and evaluate things. Okay? Does anybody notice anything kind of bizarre about my boxing? What I leave out? I left out two elements. I left out hydrogen and helium. Okay? They are so small that they aren't really in their own category. They're really part of the S block as far as their electron configurations go. But their chemistry doesn't quite align as well with any one of those columns. And in fact, their chemistry can float a little bit. And so because of that, some periodic tables will float them off of the main periodic table. Ours on the wall does not. If you go into the library or the tutoring center, the periodic table there does float those two elements. Okay? Trying to use the diagramming to help show that they're a little bit weird and they don't quite perfectly fit those patterns. Yes?
And another reason for the floating is just because hydrogen's not metal and helium is not noble. Right?
Helium is noble. Hydrogen isn't a metal. You're absolutely right. Okay, so hydrogen would almost be the one exception to that diagonal. Okay, it's not really part of the periodic table in a sense, and that's why we can get away with saying, oh, it's not an exception because it's not on the periodic table. When we look at how hydrogen reacts, it reacts very similarly to that first column. Okay? And that's going to be one of the things we'll point out here. We're naming them according to those groups because their chemistry is very, very similar. Okay? It's not just because, well, they're all in the same column, so let's put them together. Okay? They're similar for a reason, and we group them for a reason. So the chemistry behind hydrogen is very similar to lithium, sodium, and potassium. Okay?
And just from a writing perspective, like the periodic table is something that the more I know about it, the more I geek out as a writing person. Because over 100 years of its development, or 150 years of its development, we've been able to cram into its design so much embedded information, and that's why it becomes so crucial to learn about. But just from a writing perspective, it's something I keep geeking out about more as I learn more and more of how it's structured and how much is embedded in it. How much
Okay. Last thing, we'll just throw down some names just because I like some of these names. We said we needed to know the alkaline metals, the alkaline earth metals. So you're responsible for knowing those two. And you're responsible for knowing halogens and noble gases. Okay? I just like group 15 and 16 because I think their names are kind of fun to say. So the group where oxygen is, that entire column is known as the, all together now. That's why it's fun. Chalcogens. I have no idea if I'm saying it right, but hey, it's just fun. Okay? Anything underneath nitrogen is known as the pnictogens. I mean, how often do you get a silent P? Just because there's another example doesn't mean it happens a lot. Okay? And pterodactyls are pretty awesome too. So, okay. So, they're kind of neat. Phone? I don't know if that's a silent.
pH makes an F.
Yeah. In any case. So those are names, some of the names of your common group elements. You need the first two and the last two. Okay. So let's take a look at some of the physical properties. Okay. So one of the things that Mendeleev was able to do was to predict properties of certain elements. Okay. And he was able to predict those because he could group them. So what he ultimately had was just a collection of all of the elements and a bunch of their properties, and then just started saying, well, how could I organize these into something that makes sense? Right? So we've already done some organization for you, right? Everybody see that? Okay, and before anybody does so, stop reading the footnote. Okay. Well, yeah, but did you read it? There we go. Okay, we've done some organization for you. What is the organization we've done with these elements?
Physical properties.
Look at the periodic table. Oh, it's the alkali metals, organized directly as they are on the periodic table. Okay? And now we could go through and look at each of those properties, and we could potentially try to predict. So if we were, say, Mendeleev looking at this, lithium to sodium goes up by what, as far as that atomic radius? That's not proper math. Let's try that again. 0.3, right? Did I do that right? Yeah. How about rubidium to cesium? It's a little bit less, 0.2 maybe. Right? If we get rid of that potassium, what would be the jump from sodium to rubidium? Okay. That jump is what? 0.06? That's a pretty big jump there. At both the top end and the bottom end, we're getting relatively small jumps. What would that suggest? We're missing something. That's what Mendeleev is able to do. Okay? Not only is he able to say there's a hole there, there's a gap, but he's now able to make predictions about it. Okay? So we've got a test question here. What is a reasonable density for potassium? Ooh. So, where do we have to look? Periodic table of the elements is a fascinating idea, but absolutely useless. You should not be looking at the periodic table of the elements right now. You don't even need to look at the book. You mean literally on the slide? Yes. Okay, well, there's so much information on the slide. It says something about atomic mass. What did I want? Density. Why is the atomic mass there? Is the density there? Yeah. So mass over volume equals great. Do I need it? Why is it there? It is excess information. Okay? This is put on test so students go, oh my God, there's something there. I've got to use it. No, you don't. Look at what the question asks for. Ignore the useless stuff. Okay? That can be hard to do. Okay? Here, it's pretty easy because I can just go through and erase it. Okay? What could you do on a test to get rid of useless information? You could try and cross it out. What if you find out it wasn't useless? Okay. Use a pencil so you could erase it. You could cover up useless information. When you're answering question 14, do you care about what the answer is to 15? So what could you do? Take the staple out, cover up question 15, cover up question 13. So you're only focusing on one question. Okay? That can improve the odds of you successfully getting the question right. Okay? So, what do you think? I heard 0.03? 1.2. So, of course, my question is going to be, how? How did you come up with 1.2? How big did that change? How much did that one change? 0.4. Yeah, that one's actually pretty close to 0.4. Which means what should happen in there? 0.4. Would that work perfectly? No. So we'll fudge it a little bit, and we could drop it down and say we're at that 1.2 to 1.3. This is a guess using the data that you have at hand. That's it. Make sense? It doesn't have to be perfect. It's, do you have a logical flow and understanding behind it? Yeah? We good? Yeah, okay.
So since those have two significant figures, would we want to guess it to 2 decimal points?
So at this point with sig figs, ignore them.
So when
Okay.
do you care about
When do we care about sig figs? Remember, lecture is separate from lab. Have we talked about sig figs in lecture? No, so don't worry about sig figs. Does that make sense? Okay, and I know you're all like, I watched that video and it's so hard. I understand that. We'll cross that bridge when we get there. But I don't want to cross it yet. Is that reasonable?
Yes.
Okay. Before we go on too far, Greg has something to tell you in the back of the classroom.
So part of what Mike's teaching was actually a literacy thing. So you might call it rhetorical reading, but it's really being intentional about how you approach a mass data table. It's kind of like when you scan a reading for particular points. We want to be strategic in what we do. So this part is how Mike said it in past semesters. This is how I usually do it. But it's like, what's my goal in this problem? Like, what am I being asked to find? What was I given? And then how do I get from what I was given to my goal? Like, so goal given and how I get there. Mike likes to, and it became a mantra of our spring course,
Likes to
say, what do I want and what do I have? So everybody say, what do you want?
What do you want?
What do you have?
What do you have?
So what do I have? What say it with the I, sorry? What do I want?
What do I want?
What do I have?
What do I have?
And that is a rhetorical thing because it's honing in based on your intention, honing in on what is important. It's taking what you know to figure out what to accomplish that purpose. Does that make sense? Yeah. Okay.
And not take anything away from Greg, because that was a fantastic addition that you did phenomenally well on the fly. That was all about attention. Where did you all turn and look? Towards Greg, so I could advance the slide and delete the footnote again. These are your answer choices. What's your answer choice? Okay. It is reasonable. Is 1.23 a reasonable guess? Yeah, based off of the data at hand, that is absolutely fair game. Okay? So here's why I keep erasing the footnote. Okay? To add a little bit more insult to injury, we can get rid of the gray bar. The density for potassium is 0.86. Okay? So weird is a fantastic thing to state. Okay? The next thing that I'm going to ask, should you change your answer to the question?
Yes.
Phenomenal. No. The data that we had at hand said that we should go to 1.2. That does not mean we're necessarily right, but it's the data that you're using. Okay? The only way you would know to guess 0.86 or even 0.72, because 0.72 was off base too, but okay, is if you knew the answer. If you know the answer, it's a question I'm probably not asking you. Okay? I want you to think about what's given and use that information to work forwards. That's what you're supposed to be doing in science. That's what you're supposed to be doing in test questions. Okay? So what is the color of Mike's shirt is a bit meaningless as a question. Okay? You will sometimes get those, okay, because we do have some just fact things, like the symbol for iron. What was the symbol for iron? Fe. That's a fact thing. Okay? So you will see those questions, but a larger majority of questions are going to be getting you to think about the material you have at hand and trying to solve from it. Does that make sense?
Why is it 0.6?
So there was the weird statement, and then the next thing is, why is it 0.86? Okay, so they give you some information. Small irregularities are small irregularities in group trends are not unusual. Okay, is that an explanation for the why? No, they just said stuff happens. Deal with it. Okay. There are explanations behind it. Those explanations have to dig deeper into the structure of each of those individual elements and looking at those trends. I'm not asking you to do that. Okay? Does that make sense? Okay. I didn't explain why. And again, because to get into those details are outside the scope of what we're trying to do. Okay? So if you're really dying to know, we can have that conversation. It's more complex than you want.
So you just wanted to let us know that there are irregularities in groups.
There are irregularities that you're not going to be able to predict. Yep. Okay. I still want you to be able to predict. You have to have a logic behind your prediction. It doesn't have to be right. Okay. So, predicting chemical properties. Okay. We said these things get organized into columns for a reason. Okay. The alkali metals all react with oxygen, and they all react in a very particular fashion. That fashion follows the formula M2O. What does M mean? Metals. Those were all metals. In fact, they were all the alkali metals. What does the 2 mean? I need 2 of those metals to react with 1 oxygen. Right? That's what that means. So if I look at any of those metals, when I react them with oxygen, they all form this same basic structure, the same basic pattern. Okay? There was a question or a statement, maybe, Christian, did you say something about cesium being the most reactive? Somebody said something about that earlier on.
Oh, I said,
Francium. If we throw lithium into water, this is what happens. Nice little GIF. It just kind of skirts around. Why is it moving like that?
It's creating gas.
It's creating hydrogen gas, which is causing it to kind of float out of the water and float over the surface. If we now move to sodium, it's a little bit more explosive. It's releasing more energy, but it's ultimately doing the same kind of thing. If we go through to rubidium, similar process. It's igniting. What's it igniting? The gas that it's releasing, which happens to be hydrogen gas. Okay? So it's getting progressively more and more violent. When we throw in rubidium, we get a bit of kind of an explosion. It reacts so quickly and violently that it actually explodes out of the solution. Cesium literally blows the container apart. Okay? And then based off of that pattern, you might recognize that I can't even fit francium on the screen because no one has it to do this. It's going to do something very similar to cesium. I just couldn't get a gift for it.
Would it be even more?
Okay. It's even more of an explosion. Okay. Ultimately, what we're trying to see is that we see a pattern behind how these things react. If we do the same thing for, say, calcium or strontium and throw them into water, we don't see this. Why not? They're not in that group. Okay? So their chemistries are organized within those columns because they're very, very, very similar. Okay?
So these are just metals that react with water?
These are metals that react with water. Yep. Okay? They're kind of, well, let's not do that. Okay? So if we were going to talk about an exam question, okay, how could we write an exam question that would get at predicting these properties? What do you think? Ideas?
Just those properties or any other?
Any of the chemical properties. What would my answer be? Na2O. How many people think that's a good test question? Why? Why is it obvious? It's literally listed above. Yes, that's a horrible test question. I literally told you the answer, so let's change that. How about now? Is it a better test question? Okay. How would you know the answer? How do you know now? Oh, I formatted it that way in the lecture. So the reason you know this answer is because I told you the answer. I don't know about you, but that's kind of a crap question, right? Okay. Could be an easy question. Okay. You just have to memorize everything I'm saying. Did you learn anything about chemistry in that process? No. Did you learn anything about chemical properties in answering that question? No. You just learned that I said the answer to that question is that. Okay, so let's switch it up. Okay. Instead of just saying what is the formula for sodium and oxygen, how about I also add some given information? I tell you, where are we? The formula for magnesium oxide, or magnesium and oxygen, is MgO. I tell you the formula for aluminum and oxygen, Al2O3. I tell you the formula for, let's do cesium. And I need one more, don't I? I can get away with that. We'll just do that. So we said chemical properties. Members of the same family have similar chemical properties. FeO2 matches. 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 Matches, right? Every single one of the given pieces of information matches an answer. Okay? And I heard someone kind of mumble it. Kind of under the breath, sort of. I see what you did there. As in, like, that makes it a little bit trickier to deal with, doesn't it? That actually means you need to understand that principle of chemical properties. Now we have a test question. How do you answer it? You would have to know the families. You would have to use the information you have at hand. What is the information you have at hand? Periodic table. And we could pull up the periodic table. We have an extra layer here that I didn't even mention. What else do you, well, you don't have to know this. We do kind of need to know that sodium is Na so that we can find that proper connection. So there's sodium. If we go through and look, we had magnesium. Next to it, we had aluminum. We had cesium way, way down below it. We had iron somewhere in here. Okay? And for those of you who are looking at my drawing and being like, God, what the hell is he drawing? I'm drawing the periodic table without all the other elements in it. Okay? What is my family for sodium? The alkali metals. Which would be which? Cesium, because it belongs in the vertical column, or our family. Cesium is going to be the one that tells me my answer. I look up my cesium, CS2O. I know my answer is B. Make sense? Okay. How do you look it up on your test? I have to give you this information, and that's exactly what I'll do. I probably will not give you the example of the alkali metals because we just did it, and what I'm trying to do is test your understanding of the principle, not just did you memorize what I just said. Make sense? Getting a feel?
Did you guys all put that process in your notes?
Right.
I didn't see too many people writing, that's why I asked. Hey, we're absorbing.
That is one of the challenging things within the chemistry class is what do you write? Okay, what do you put down? Okay? And what a lot of times people will write down will be the final solution. The final solution was not how we got to the answer, which means when you go home to sit down to try and solve a question, what do you try and write down? The answer. If you don't know how to get to the answer, you're dead in the water. You got nothing. So what you should be taking notes on is not the answer, but all the little questions along the way. What did Mike ask before he wrote something? Because that question is what you need to ask yourself. Okay? And usually those questions that I'm asking before we write something down are easier than the original question. Usually. This one was a rare exception because we flipped it. Instead of saying, how do we solve this question, we said, how do we write this question that would allow us to get at that thought? Okay? So you're going, that is way too hard for me to do. I don't want to ever do that again. Anytime you see a multiple choice test, someone had to come up with a question, that exact process. If you can get that figured out now, guess what you know? Every question on every test, ever, you can now answer virtually any test thrown at you. Okay? That requires more work, more practice, more skill, but it builds you to a place where you can do this. Okay? If all you're worried about doing is getting the answer to the question asked, you do need to do that. Okay? But you're going to be one step behind. Yes, yeah.
So do we have to memorize then LI to O?
Nope.
You
Nope.
don't give us that information.
What I will give you is exactly what's up here, red and blue.
Okay, so like if it was the alkaline earth metals, you'd give us the BE, MG,
Okay.
CA.
So what I'm hearing is, what's another question?
Yeah.
What other question we want to ask? We want to do alkaline earth?
Yeah.
Okay. Let's do the alkaline. Alka? Yeah, whatever. No one laughed, so clearly no one saw. Alkaline earth?
I think that's supposed to be a picture of the Earth. And
Oh my God. I see.
that's
What's the little tail coming? It's the edge.
That's the CO2 emissions. So let's go through and take a look at our alkaline earth solve. Okay, so given information, I will give you that magnesium chloride is MgCl2. Aluminum chloride. Oh, this one's a lot easier. Whoops. Oh, well. Sorry. It'll work. Nope, let's not do that one. Let's do that one. Thanks, William. And let's go through and do. Okay, so given, I give you that information. Yeah. What is the formula for gallium and chlorine? Gallium's a little bit tricky because I don't think that's on your one to memorize, is it?
No.
Oh, sorry. We'll add a hint. Okay. Any guesses what answers you will see as answer choices? Oh, I repeated that one.
Nope, you repeated it.
Does it matter? So what's our answer choice? Admittedly, I didn't go through and label them. A, B, C, D. B gets an answer, and that would be the correct one. What are we looking for? Gallium, so Ga, and I need to figure out which element is in the same family. So I have to find gallium. There's gallium on the periodic table. Magnesium, is that in the same family? No. Okay. Aluminum. Yep. So aluminum, I might stop right there. Okay. Usually, if you're spent on time, go ahead and stop there. If you have time, you should go through and check the rest of them. Oxygen? Nope. And nickel? Nickel can be a tricky one. Why could nickel be a tricky one of this?
Because it's horizontal.
It's in the same period. The trend is through families. Okay? Through that vertical column. Okay?
You could phrase the answers in like the other way, so families like us and periods or something.
The chemical properties only hold true through a family or group, not through a period. Does that answer your question? Okay.
So is that, are those, that makes sense? I don't need to say balanced. Like, are those?
They are all technically correct, yes. Yeah. But we haven't talked about that, so we can't address it. Okay. Kind of makes sense? Yes? We got one yes. You said that just loud enough that I'm positive it was recorded right as I clicked next. Why is it 3? Okay. If we looked through our pattern, we had AlCl3, and the question was gallium. Why are these our pairing and not MgCl2, OCl2, what did I say? Nickel Cl4. Why is that the pairing? So, and this is one of the things that gets a bit dicey. Some people are jumping out, oh, well, it's the geometry of the atom. We haven't talked about geometry. You can't use geometry. Right? It's the amount of electrons that each of those have. Have we talked about electrons? No, so you can't use that either. Okay? This is literally coming from the organization of the periodic table. Okay? Those trends that you guys are using are trends that are already buried in the periodic table, but they're also things we haven't addressed. Okay? So why are we getting this is our answer, GaCl3? Where is gallium? Where is aluminum? They're in the same group. And what did we say was true about the same group? Can I go back? It's over there. Members of a family have the same chemistry. Okay? It's that trend. All you got to do is no vertical column. You have to look at the vertical column. That's where your trend is. Okay? So gallium versus aluminum. Okay?
If it helps you to think of a family tree working vertically, maybe.
Sure.
Why? Isn't it just columns and groups?
Groups are still
So
vertical.
So that's how you just
It's not just
So-
anything.
There's an interesting question, okay, which I believe is what Greg was trying to get at too, and I'm hearing a few other people jump at. Why did I say GaCl3 and not GaCl2 or GaCl4? Okay, we could go through and say, well, those chemical properties belong somewhere else. Okay, why am I able to say that it's GaCl3?
We have given
Because I've taken the class before. I have the chemical knowledge to know what the formula is going to be. You don't have that knowledge yet. So what do you need? The tools to be able to figure out how to get that knowledge. What was that tool? Chemistry within the family is similar. Okay? That's it. With that knowledge and that knowledge alone, I can go from aluminum AlCl3 to GaCl3. I'm allowed to make that statement because they're in the same family. That is the reason I'm allowed to do it. Why did I know the specifics of the 3? That's more chemistry that we haven't gotten to yet. So hold your breath. Don't hold your breath because it's going to take longer than that. Okay? Just hold that enthusiasm until after we've talked about why we know we need 3 outside of the context of this. Because even that doesn't hold true for some cases. Okay? So you have to have some other secondary knowledge to know when these things work and when they don't. The questions that I give you will, guess what? They will work. Okay? And I won't put you in those cases where you have to know 6 billion different things to be able to process it. I want you to be able to understand that chemistry within a family is similar, which means when they react, when I mix multiple atoms, as long as I'm mixing the same types of atoms, I'm going to get the same formulas. Justin.
I remember you mentioning very briefly at the beginning of first week, maybe the second, something about for those of us who never took chemistry in high school, there's a certain amount of curricula that we're expected to already know and have a base knowledge of.
No. So those of you that have not had chemistry before, I assume you don't have chemistry, which is why I have to give you this context. For those of you that have had chemistry, well, but why know that? Because of the charges. Dude, you know more chemistry than somebody else. You're using a different rule set to get to that answer. That rule set will work sometimes, not always. So if you haven't had chemistry, I'm giving you the rule set. This is what I'm telling you to use.
Just a little bit. For those of us who haven't had chemistry, it's a little bit different in working the logic backwards. Starting with a bunch of unknowns and then working back, you know.
Yep. And with that question, though, and so that's going to be the problem, is the people that already have it are starting to apply things, which is good, to the course. We haven't covered that connection. Talking about electron configurations is a phenomenal thing. What the hell is an electron configuration? Have you had chemistry before? What's an electron configuration? Then a discussion of electron configurations now is irrelevant. What is relevant? Within a family, the chemistry is the same. That's how it works. So that might be the confusion, is that you're listening to somebody else say, oh, well, you could do it this way. If we haven't talked about it, you should be really careful listening to what somebody else thinks they should do to get there, because we haven't addressed that foundation. Okay? Particularly if you don't have that older chemistry. Does that make sense?
So you said within chemistry.
Within the family, chemistry is the same. That's why we can see these formulas all come out the same, because lithium is an alkali metal. Sodium is an alkali metal. Potassium is. Rubidium is. Just checking. Rubidium is an alkali metal. Cesium is an alkali metal. That's why the formulas are the same. No electrons. Okay, remember, Mendeleev did this organization before electrons. You can too. Okay? Which I think I'm potentially going to regret, because I'm like right about to talk about electrons.
But it's good to walk through this process connected
Yeah.
to, like, this is modeling the scientific method, the scientific process of discovery. Sometimes you only know this hazy idea about it, or kind of the certain tangibles, and you don't always have the data, but then you go get the data to confirm. Like, that's part of the scientific process, is taking what you do know and trying to figure out other better ways to understand it.
When Mendeleev organized it the way he did, when we discovered new things, those new things also had to be reconciled within the periodic table. If those new things were not also explainable in the periodic table, what does that say about his table? It's not good. It's wrong. Okay? So that's one of the things that is nice behind his table, is it is so good that it actually has information that we haven't talked about yet already layered inside it. Okay? I'm really regretting this slide sequence because you guys are a little dodgy on this. It's okay, but I think this is only going to explode things. So we're just going to start into it slowly and we'll see how it goes. We're going to talk about 2 periodic trends here. Okay, well, 1 periodic trend. Okay? the size of the atom, okay? When I talk about the size of an atom, I'm talking about its atomic radius. What am I referencing about the atom when I talk about its size?
Its physical characteristics. How much the electrons?
Am I talking about the electrons? Or am I talking about the protons? Am I talking about the neutrons? What am I talking about when I talk about size, atomic radius? The electrons.
Something round.
The protons and neutrons do not contribute to the size, the atomic radius of the atom. And you're like, but they're part of it. That's true. The protons and the neutrons, for those of you holding up little symbols, yeah. We're a marble inside the superdome. Are you really telling me that a marble contributes to the size of the superdome? Okay. Not really. Okay, so what we're talking about is the electrons. Okay, that becomes challenging because when we move into atomic radius, we are talking about the size of the atom, and that ultimately has to do with the electrons. Just the electrons.
So that's
Okay,
the size.
sort of. And that's where we have to be careful with this. So there are two trends for the size. What happens as we move from hydrogen to helium? What happens to the number of electrons? It increases. It goes up by 1. What might you guess about the size of the atom? Why should it get bigger? There's more electrons. How about we go down the column? Hydrogen to lithium. There's more electrons. So what should happen to the size? It should get bigger. Should. Okay? So let's take a look at the easy one. Atomic radius increases as you go down a group. A group was that vertical column. As we go from hydrogen to lithium to sodium to potassium to rubidium to cesium to francium, it gets bigger. Thank you. Saw that. Francium is larger than hydrogen. Okay? Notice in this statement, does it say why? No, and for a very important reason. Okay? I want you to take a stab at it. Why do you think it gets bigger as we go from hydrogen to francium?
More potential energy held in that bigger order.
At that point, I really just think you're using big words to hope that somehow it's going to...
The more energy in there, the bigger the orbit, right?
Just working with human information?
It gets more.
Not quite. So the size could contribute to reactivity. Remember, francium, we didn't even see because it explodes. Okay, why does it explode? It's so large that when it reacts, that outer part is so far away from the nucleus, it just flies off. Super reactive. Whereas the hydrogen is so small, it's right next to the nucleus, it cancels out that charge very closely. It's harder to react. Okay? Why would it get bigger? What contributes to size? Electrons. What happens as we go from hydrogen to francium? And now you guys are probably like, I'm not going to say it because you were just making it sound like that's not the answer. You're right. I am doing that. Why might it get bigger? Because more electrons. Okay, so this was down a group. What do you think the very next thing is going to be? Cross a row, which would be a period or a series. Family is still vertical. Okay? What happens to the amount of electrons as we go across a period, left to right? What happens to the amount of electrons? It increases. Lithium to beryllium. Lithium has 3. Beryllium has 4. As we go left to right, what happens? We get more electrons. What did we say happened when we got more electrons down a group? It got bigger. So when we go left to right, what's going to happen? It's going to get bigger. Except it doesn't. It gets smaller. Okay? These trends are true. Okay? These are true. I have not put explanations why yet. Okay? What we are talking about is the electrons and where the electrons exist. Okay? Electrons have energy, and yes, they have potential energy. And it is the contribution of where the electrons exist that is contributing to size. Do you know where electrons exist yet? And because we're on the same wavelength, because I know you haven't had chemistry before, do you know where electrons exist?
I know a little bit about quantum mechanics, so you're asking the wrong guy.
Well, that may have been a bad person to ask. They exist outside the nucleus. Where outside the nucleus? Have we said? No. We haven't said. Okay? It's in the reading, so we would have to apply what's going on with that reading into this. How many of you... let's not do that. Okay? If we take a look at pictures, down, we're getting bigger. Left to right, what's happening? Getting smaller. Okay? The down one seems to make sense. More electrons, getting bigger. Left to right, we're still getting more electrons, and yet we're getting smaller. Okay? This is a very challenging one to explain. Does someone want to take a swing at it? With the extra caveat that I'm pretty sure the textbook effed it up.
I'll still take a swing at it.
Go for it.
It's because the protons and neutrons have a larger mass that kind of conducts a stronger field that brings the electrons in closer to it, making the atomic field smaller.
Okay, did everybody catch that? No. Okay, so let's run through that. What he's saying is that when we move left to right, we have
More protons.
more protons. What charge are protons? Positive. So as I move left to right, I have more protons. So what are those protons going to do to the electrons? They're going to attract them. Which means when I move left to right, it should get smaller because there's more protons. How many protons does hydrogen? Let's do lithium. Lithium. Switch it up. 3. How many protons does cesium have? Some people are already laughing. Why are you laughing? Why are you laughing? Oh, okay. What was David's theory left to right? It gets smaller because more protons. What happened down a column?
More protons.
Does the theory hold water? No. So halfway, but just as halfway as the other one did. Okay? So both theories are missing something. That something has to do with where electrons are allowed to exist. Okay? And they exist in distinct things called orbitals, at different energies. And it is how we transition between those energies that contributes to our size. Okay? So what we're going to have to do is kind of take a break away from atomic radius and now go into what the hell are electrons, what are orbitals, where do they exist, what is going on behind that. Okay? And yes, Sierra, I'm right there with you. This is a bit of like a beating yourself in the head with the desk. Head to the desk, one of those things. Electron orbitals are very challenging for students to grasp and deal with. Okay? What we're looking at is probabilities for where an electron can exist. Okay? And they exist not in a way that we would typically expect. They exist both like light as a wave. Okay? So that means when we turn on the light, the whole room fills with light. It's not directed in one pinpoint direction. It's not a particle. Okay? But they also have a particle aspect behind them. Okay? Imagine if the light was like baseballs. Okay? They come flying out in one direction, also known as a laser. Okay? Sorry. Austin Powers just kind of like flashed. So, the atomic radius trend is challenging to deal with electrons. Okay? I will absolutely ask about that because it is a challenging one to deal with. I will also ask, do you know what the trends are? Okay? The trends go rather nicely. Okay? It decreases up a column or it decreases left to right. Because I give you a periodic table, what could you do as soon as you get your test? Write the trend down. Guess what you don't have to do? Memorize the rest of that information. So if you write it down, you can minimize the amount of stuff that you have to memorize. That's pretty cool. test-taking strategies 101.
Right.
Okay? We could also do metallic character. You'll notice they're trying to reference metallic character, the same kind of thing. I don't really like doing that, but it's also true. The lower left is the most metallic. The upper right is the least metallic. Okay? So, bouncing back to chapter 4. Remember, electrons, waves, and particles. So the first thing we kind of have to address is waves and how we would even see or represent some of this. Okay? Don't freak out too much by the numbers or the equations here because I'm not going to ask you to do really anything with those. Okay? So when we go through, we've got wavelength and we've got frequency. There's two ways that you can represent a wave. Wavelength is peak to peak. Okay? How long or that distance is. Frequency is within an individual time frame or an individual range. How many peaks do I get? Okay? They are inversely related. The longer the wavelength, okay? I always have problems with inversely related. Longer wavelength, less frequency. Okay? That was actually right. Okay? We can correspond this back to this term here, an equation. E equals h nu, the Greek letter. Okay? That's the frequency of light. Okay? So sometimes we might go through and specify that light is being involved in something, and we could just write h nu. What we're really trying to say is that's the energy of light in our reaction. Okay? Yes?
So can those two equations work for both low and high frequencies? Or
Yes. Okay? Light, or visible light as we know it, makes up a very small part of the radiant energy spectrum. Why do we call it radiant energy spectrum? Because it used to be called something else. What else did it get you called? The electromagnetic spectrum. Why do we switch to radiant? Why do we switch to radiant as opposed to electromagnetic spectrum? You heard of an MRI?
Yeah.
Yeah, an MRI is actually an NMR, nuclear magnetic resonance. If I told you you needed to get into an NMR where there was a nuclear term associated with it, what are you going to do? You're going to say, no, I don't want to die. Dude, it's the exact same thing. Nuclear in that case is referring to a nucleus. We're looking at nuclei, that's it. It scares people. An MRI is called an MRI and not an NMRI, not because we decided there were too many letters. It was because the N scared people and they didn't get into the instrument. That was it. Why do we switch to radiant energy? Because electromagnetic sounds a little scary. Okay? You're not scared by that, that's cool. You weren't being targeted. Okay? Somebody else was. So, our radiant energy spectrum. It spans all the way out from cosmic rays all the way down to radio waves. Okay? Visible light makes up a tiny little section within it. Okay? What I want you to be able to do is to think about our visible light and know something about energies associated with it. Which is the highest energy, purple or red? Red. When you step outside in the Arizona sun, we do tend to freak out a little bit, right? And what do we tend to protect ourselves with? Sunscreen. Because it is blocking what?
UV.
Ultraviolet rays. Why are we concerned about ultraviolet light? Why does it give you cancer? Because it is high energy. Which color is more energy? Purple or red? Purple. Or if we want to get really specific with it, violet. Okay? The red light we are less concerned about because it is lower in energy. Okay? So we can use our very well thought out fears of ultraviolet radiation killing us and tying that back to the energy of our visible light spectrum. What are the colors in the visible light spectrum? Roy G. Biv. Okay, conveniently written backwards here, but we'll deal with it. Red, orange, I'm not going to use the yellow pen. Green, blue, indigo, second blue. Right? Who even knows? And violet. What I call indigo? Second blue?
No, the Roy G. Biv.
Roy G. Biv. It's up here backwards, conveniently. Okay, but one way to go through and memorize it as if it's someone's name. Mr. Roy with middle name G, last name Biv.
Who here has heard that one before? Raise your hand. Art?
Yeah, I could see that in art class. Okay. So there isn't any red orange. Red orange isn't a color in this. Mauve. Puce. Like, what the hell are those colors? Those are valid colors. I wouldn't be able to pick them out of a lineup, but those are valid colors. They're not in the rainbow. All colors are in the rainbow, right? We have arbitrarily gone through and said, this is red, this is orange, this is yellow. There's no transition between them. Why? We're trying to simplify our thought process behind it. Okay? But we do need to realize that this is a full spectrum. It covers all of those colors. If you've taken art classes and talked about shades, don't bring that in. Okay? Keep it simple. Okay? So we have those sections behind it. We now know that violet is the high energy one, and we know it's the high energy one because it is closest to ultraviolet. It's even in the name. Okay? Make sense?
So it's the highest in concentrated energy.
It's just the highest energy. It has nothing to do with concentration. Okay? So why do we talk about this? Well, we talk about this because what scientists went through and do, and what scientists tend to do with a lot of things, is they discover something cool, electricity. And they're like, well, what happens if I take this electricity and do something with it? Hey, lab partner. Yeah, that was kind of funny. Okay? They do the same thing to elements. Okay? And they did it with hydrogen. Okay? So they take a tube full of hydrogen and they filled it with a bunch of electricity. They put a high voltage across it. Okay? When hydrogen gets electrocuted, it emits this weird purple light. Okay? Well, we then went through and said, well, let's pass that through a prism, because what do prisms do? They separate the light into all of the wavelengths, so we should be able to see it. So if it's a purple light, what would we expect?
Big purple band.
A big purple band. And instead, what do we get? No purple band. We get a purple line, a green line, blue-green line, and a red line. What? But it was purple light. Why is it not just this purple band? A continuous spectrum. Instead, we're seeing this discrete spectrum. Okay? That's a bit puzzling and a little bit weird. Okay? So how did we get to this? What did I have to do here? How did I excite it? With electricity. Okay? I applied a high voltage current to it. What is electricity composed of? Electrons. So what I'm doing is pumping electrons into this system, and it's causing this weird light. Well, maybe that's just what all matter does. Well, no, we put in different atoms, we get different bands. Okay? So something about that has to be the case. And because we're putting in electrons, it is probably the electrons that are doing this. Okay? So we have to come up with a theory to explain this. Because at this point, where did we say the electrons were? We just said outside the nucleus. Okay? Which means they have all of the energies accessible to them. If they're very close to the nucleus, they're very low in energy. If they're very far from the nucleus, they're very high in energy. And they can exist at all states in between, which means I should see a band of colors. Distinct lines means those electrons can only exist at distinct energies. Okay? This gets put together by Niels Bohr. And so what he postulates is says, you know what? We've got a nucleus. The electrons exist in orbits around the nucleus. Okay? Electrons cannot exist in between orbits. It can only exist at an orbit. Okay? If you've ever seen the Quantum Physicist for Babies, I'm about to do that. I apologize, but it's a pretty good example. Here's an electron at a low energy. Here's an electron at a high energy. Electrons can exist at those individual lines, but an electron cannot exist in between. That's kind of where the book stops. Ta-da! Okay? How does this explain what we're seeing with the atomic line spectrum? Okay? Well, if we look at hydrogen, it has how many electrons? 1. And where would I expect that electron to exist? The highest energy possible or the lowest energy? Lowest energy. And we all know that because when we walked into this room, what did we do? Yes, you breathed. Y'all are currently doing it. You sat down. No one's standing. Why not? It's more than weird. It requires energy for you to stand. If you sit down, you can be lazy and you could fall asleep. That's cool. Okay? If you're standing and fall asleep, you fall over and that hurts. Okay? So we can sit down so we have the potential option to relax and hopefully allow our minds to focus on who's talking instead of worrying about standing. Okay? So here's our happy little hydrogen atom with its single electron. Then what happens? Bohr comes in with the cattle prod, pumping tons of electrical energy. What happens? Adds energy to the electron. This is a low energy state. Okay? There's a cattle prod under one of your seats. It's a small one. It's just one of those little finger buzzers. Okay? What do you think is going to happen when I push the fire button?
You're going to instantly go to another orbit.
Oh, no one was sitting in it. Well, that takes all the fun out of it. I'm just kidding. So what happens to the electron? It jumps. It absorbs that energy and it jumps. How far does it jump? Depends on how much energy I put into it. Okay, let's just say it jumps to the next one. Okay? What's going to happen to that one person who jumped in this classroom because they just got, the little electric buzzer? They're going to get probably pretty pissed. They might laugh it off because, haha, Mike, that was hilarious. Okay? You can hear from my lawyer soon. And then what are you going to do? Sit back down. You'll probably remove the chair. Okay? But you'll sit back down. Okay? So the electron will naturally fall back down. When you got up and down, you also changed energy. When you got up and sat down, you released energy in the form of... For those of you who are like, I don't really know. I don't think that's really happening. Whenever you get some time, feel free, sit up and stand down like 100 times. And then you can come back and talk to me about where your energy went. Because it'll probably be a little more obvious after you do it a couple times. Guess where this energy gets released when the electron jumps back down? As light. The energy difference between those orbitals happens to directly correspond to the wavelength of the light coming out. Those are due to electrons jumping back and forth between orbitals. Okay? I get super excited about this and talk way too much. I apologize. I should stop.